So we are going to talk about a new definition for acids and bases. So what we've learned as a definition previously is that as an acid, if you dissolve in water, what you're going to produce is H plus. If you have a base and dissolve in water, then it will produce OH minus. And so before we get into the definition for Bronsted Lowery, we have a new term for H plus, and that is just calling it a proton. And that may seem kind of silly to you. You're like, wait, that's a subatomic particle. But if you think about a hydrogen atom and break it down, it consists of one proton and one electron. Now, if it gives up its electron and becomes H plus, all it is one proton. So H plus is a proton. So we're going to refer to it as such. And so thinking about this next definition here, you might see on the worksheet B/L, that just stands for Bronsted Lowery. And we're going to just discuss in terms of protons. Now, an acid is a proton donor. What it means is you're an acid if you have an H to give up. So an example would be hydrochloric acid. So if we were to think about how this interacts with water, it has this hydrogen that it can donate to the water. That becomes H3O plus, and we are left over with Cl minus, chloride ion. Now, as you probably could assume, bases become proton acceptors. So they're substances that have the ability to take a hydrogen. So one that we haven't talked about yet is ammonia, NH3. This is a special compound. Reason being is it doesn't have an OH and it's not negatively charged, but it can still form ammonium. And so you guys should have seen this ion before from your table E's and your blue packets when we talked about polyatomic ions. And the other thing that's made is hydroxy. So the reason why it can do this, NH4 functions very similarly to water, where it creates that coordinate bond. Now, we have some special substances that could donate or accept a proton from where it's at. And so we're going to call these amphiprotic. But you may see this in other places as amphoteric. So what we're going to do this next portion is identify, is this substance an acid? So it donates protons. Base, it can accept a proton, or amphiprotic, it could do both. So starting off with HCl, does it have a hydrogen on its left it can donate? Yes, so we're now, does it have a charge? No. And is it either NH3 or H2O? No, so it's only an acid. So really the exceptions of being a base are H2O, NH3, or having a charge. This next one here, does it have a charge or the ability to accept a positively charged hydrogen? Yes. Does it have a hydrogen to give away? So it's only a base. This next one here, do we have hydrogens we could donate? Does it have a charge? Only an acid. Last one here, do we have a hydrogen to the left? Nope. What about a charge? Amphoteric. Or protic. I mixed up the two. No, one of them is, I think, a little bit more of a blanket term, but you'll hear both. Okay, any questions about these? All right, so as we've seen, our bases do not have to be negatively charged. We saw this with water, where if we had one molecule of water plus another, they're going to make H3O plus and OH minus. Now, with this reaction, that means one of these is going to act as an acid, one of these is going to act as a base. Either one of them could have, one of them will just make that or take on that role. And so the other exception to the bases that do not need to be negatively charged is going to be ammonia. Otherwise, you guys are going to see them be negatively charged. And so these special bonds that they make, so NH3 acts as a base and makes NH4 plus. And so we call them coordinate covalent bonds. And again, showing you the structure of what this looks like. If we have a normal water, we have oxygen with 6 valence electrons. This other proton just hangs out, gets attracted, and oxygen goes, hey, I'm going to donate you 2 electrons. You can share both of them with me, versus one atom sharing one and one atom sharing the other. And so this is a very special thing that happens. We call it our coordinate covalent bonding. So water and ammonia do this. These are special bases that are not negatively charged. Now, we're going to kind of identify what are called conjugate acid base pairs. And so if you have an acid, so something that can donate a proton, and it does, what it forms after donating that proton is called this conjugate base. I think I'm also trying to see how many colors I can use in one lecture. I think we're on to 3 now. All right. On the flip side, if we have a base that accepts a proton, that form is called its conjugate acid. And what's really neat about this is if you have a weak acid and it donates its H, the conjugate base it makes on the other side of the reaction arrow is strong. So the strength of the conjugate is the opposite from the original. So strong acids make weak conjugate bases and vice versa. And so first we're going to work on kind of identifying, I'll look here actually at this reaction here. So if we have an acid and a base, on the right-hand side, which is the acid, H3O plus or OH minus? Which one can donate hydrogen? So this is the acid, this is the base. If you were to think about pairs, the acid on the left side pairs with the base on the right. This is an acid-base pair, because this is what happens after it does the action that was initially defined. If I define water as an acid, it has to lose an H. After it loses an H, it becomes OH minus. If a water is going to act like a base, collect and accept another hydrogen, it's going to look like H3O plus. So it's about kind of the pairing up, and hopefully it'll make sense after a few examples here if it doesn't already. So let's first just work on finding the conjugate base. So we know we have an acid here. We've got a hydrogen ready to go. What do you think the conjugate base will look like then? What has to happen if it's an acid? It has to do what with its proton? Donate it or lose it. So writing a conjugate base is losing the hydrogen. So acid conjugate base. This would be a pair. Now, if I tell you that HNO3 is strong, what does that tell you about the reactivity of NO3? It's weak. So this is a weak base. Now let's do the flip side. I'm telling you I have a base. You can also tell because it's got that -1 charge. If a base accepts a proton, the conjugate acid will be plus 1 more H, HCl. This is the conjugate acid to Cl minus. Now, if chloride is weak, what does that mean for HCl? Strong acid. Any questions on this? Okay. So What if we have something that's amphiprotic? We know we can donate this hydrogen, but we know we can also accept one. So when you're writing the conjugate acid base pairs, you have to write both. So the conjugate acid, what would that look like? So think about if you're trying to find the conjugate acid, what would happen if this acted like a base? So then what should its conjugate acid look like? Beautiful, H2SO4 with no charge. Because you got to remember that each hydrogen's +1. So if you add another one, it cancels out this -1 charge. Now, if we're trying to find the conjugate base, that means this is acting as an acid. It donates its last proton, which means we take away a -1 charge, or sorry, we take away a +1 charge, which leaves us with SO4 -2. So if you lose a hydrogen, greater the negative charge. If you add hydrogen, you're adding +1. So you have to think about charges for these. Any questions on that one? Okay, so what if both of these things can act as an acid or a base? What you're gonna have to do is compare their relative strengths. You guys remember what our measure of acidic strength? Not quite, we use a constant that helps. Ka, exactly. So Ka, if you look these up for both of these things, it shows how strong they ionize. So Ka for HSO3 -1 is 1.1 times 10 to the -7. For HPO4, we have 2.2 times 10 to the -13. Which one of these will act as the acid? What? Acid base. The reason being, the higher the Ka, the stronger the acid. And so that's going to be the one that dominates, saying, nope, I'm going to give you my proton. So now let's predict some products. If we know that HSO3 is the acid, it's going to donate its H and become SO3 -2. That means the other species is going to accept that proton and become H2PO4 -1. So every time you accept a hydrogen, it's accepting a +1 charge. Good. All right, any questions about that one? So technically, this is now a base, and then this would be your acid. And if you were identifying the base pairs, this acid would go with this base would go with this acid. Does that make sense? Because technically SO3 -2 can't be an acid because it doesn't have an H to donate. All right, any other questions? All right, let's identify some pairs. So if you have something that has an ion like chlorine, and on the other side you have chlorine, these are automatically going to be a pair. Does HCl have a hydrogen to donate? Yes. Can it be a base? So this has to be our acid. Chlorine minus is going to be our base. So this is our first acid base pair. We kind of connect them like such. Now, you can only have one acid and one base on each side. Obviously, you can have things that could identify as either, but they're going to pick a side. So in this case, we have an acid, which makes this water the base. And we know it's a base because its pair on the other side shows it that it accepted a proton. So if H2O acts as a base, it accepts a proton, and its conjugate acid form is H3O+. Any questions about this one? Okay. For this one here, So we know that we're gonna have a possibility for NH3 or H2O to act as an acid or a base. But if you look on the right-hand side, NH3 and NH4 are gonna pair up. They both have a nitrogen with it. How did NH3 act? What did it do? Did it lose a proton as it went to the other side, or did it gain one? Gain one. That makes NH3 our base, NH4 plus our acidic form. If we have NH3 as the base, that must have meant that H2O acted like an acid and donated a hydrogen. If you lose a hydrogen, you create OH minus, which is the base. Any questions about this? All right, so feel free to work on that worksheet there.